to the cloud, which is the phrase of the day is to the cloud. You probably already guessed that, but that's what it is. So that's 3 bonus points for that bad boy right there, that phrase of the day, to the cloud. Just input it in the same place that you would put the word of the day. All right. So determine if the following vector fields are conservative and find a potential function for the vector field if it is conservative. All right. So we'll start off with the conservative part. Now, we've already kind of tackled some of this in terms of the process, because if you look at the example 2 on the previous page, that's the same one, so we can kind of bypass that step. But example 1 is different. All right, so we still have to work with number 3, but we already know that example, that number 4 here, since it's based off of example 2, it's going to be conservative, but we still need that information. All right, so I'm just going to do a lot of copying and pasting when it comes to that one, but this one we're going to take from scratch. All right, so the first thing is to look at P and Q. So what I mentioned before is that P and Q can also be thought of as the first order partial of the vector function f with respect to x and with respect to y, respectively. We're going to need to know, we're going to need to have that information as we go forward. So I'm just jotting that down. So 2x cubed y to the 4th plus x, 2x to the 4th y to the 3rd plus y. Those are 2 relevant functions. All right, so I'm going to find the first order partial of p with respect to y and the first order partial of q with respect to x. So with respect to y, that x is going to go away, but the y to the 4th is going to become a 4y cubed. So we're looking at 8x cubed y cubed. Now, we won't have to bother with a potential function if this one doesn't also end up being 8x cubed y cubed. All right, so we'll see. All right, so here we can ignore the y, take the derivative of x to the 4th, which is 4x cubed. 4 times 2 is 8, so 8x cubed y cubed. All right, so therefore f is conservative. All right, so we're kind of off to the races here. All right, now what we do is we choose one of these two, whether it's P or Q, to work with. We need to solve the differential equation involving partial f with respect to x or partial f with respect to y. All right, because the antiderivative of either of those will give us a function f related to the appropriate variable. All right, so basically it's partial integration rather than partial differentiation. All right, so what we're looking at, that 2x cubed y to the 4th plus x, that is the result of a step of partial differentiation. We want to undo that. All right, so I would take, doesn't matter, they're both the same quality of function. So I'll take the partial f with respect to x, which is 2x cubed y to the 4th plus x, and I'm going to solve that differential equation for f. All right, and you're going to see some things familiar and some things that we can now kind of tackle. All right, so you're going to get it into differential form. So 2x to the 3rd y to the 4th plus x dx. Anti-differentiate both sides, and we're going to get f is equal to, we're doing this with respect to x. All right, so everything else is going to stay put. The x is going to become, or the x cubed anyway, is going to become 1/4 x to the fourth. So 1/4 times the 2 is going to be 2/4, 1/2, x to the fourth, y to the fourth, plus, for quality, plus 1/2 x squared, plus some function that would differentiate to 0 if we took the partial derivative with respect to x. So that function would be some function of y. We don't know what that function would be, but it doesn't necessarily have to be a simple constant. It could be a function. We learned that towards the end of the last unit. All right. So now what? We got to solve this is the most general form of the solution of a differential equation. So this c of y could be simple, or it could be something very, very complicated. If c of y is equal to 0, then it's going to be anticlimactic, but it could be a whole lot more complicated than we think. All right. So what we have to do is figure out what that c of y is going to be equal to. Now, it doesn't look like we have much information to work off, except we kind of do, because if I take the derivative of this function, which is itself the antiderivative, the partial integral with respect to x, if I take the derivative of this, the partial derivative with respect to y, then I can make this into, it'll have to become a c prime of y, but I have a relation that would allow me to solve for this, because I know what the first order partial with respect to y is equivalent to. All right, that's this guy over here. So I have at least an equality to work on. All right, but this process only works out if it's conservative, because, and you'll see in the next step, you get some nice cancellations that would never happen unless it's a conservative vector function. Right. So the derivative of this with respect to y now, right, so the x parts are going to disappear. I'm looking at that y to the fourth becomes 4y to the third. 4 times the 1/2 is going to become 2x to the fourth y to the third. That 1/2 x squared is going to 0 because it's with respect to y. And the derivative of c of y, well, it's a constant function of y. With derivative, the derivative with respect to y, it's, the variable of interest is y. So in the context of x, it's a constant function, but in the context of y, it's a function of y. Right? So c prime of y is what that should become. Right? Since I know that partial f with respect to y as given was 2x to the fourth y to the third plus y, I now have a relation between these two expressions that would allow me to solve for, well, I want c of y, but I'll settle for c prime of y. All right? Because I can now say that 2x to the fourth y to the third plus c prime of y is equal to 2x to the fourth y to the third plus y. Cancel, cancel. And now I have c prime of y is equal to y. All right. Again, I need y. I'm sorry, c of y. I have c prime of y. All right. So I can anti-differentiate this. I'm going to put it in differential form though first, because c prime of y is the same as saying dc dy. It's a function of one variable, so we can go d's instead of partials. That's the same as saying dc is equal to y dy, which makes c equal to 1/2 y squared. Now, I know it gets a little weird. We call this c, but it's going to be another c. It's going to be plus c. So what we could do, just to kind of keep this organized, we call this c of y. And this would be just an ordinary constant c. right? So now we know what C of y is, and we therefore know a function f whose gradient functions, gradient vector would be p comma q, 1/2 x to the fourth y to the fourth plus 1/2 x squared plus, instead of c of y, I would now say 1/2 y squared plus c. Now we would need some other kind of condition in order to figure out what the value of c is, but this is an accomplishment in and of itself. So we kind of rejoice in the fact that we even got this far. All right. But yeah, in order to figure out what the value of c is, we would need some other condition. But what this gives us is a multivariable function. So this is the equation of a surface whose gradient would be, if you found the partials with respect to x and y, the gradient vectors, the gradient vector with the component p and q that were given. All right. So this is the surface that would have the path of steepest ascent or descent, depending on how you look at it, defined by p and q. Right. But it's using this approach to help us get there. All right. So I'm going to grab the work from the previous page, bring it over, because again, this is just, in part repeat for number 4, but also it has some stuff that we have to tack on. All right, so I'm just going to kind of pop this down here so we have it to work off. All right, now just going back to number 3 for a second, you could have, if you wanted to, determined the same result if you had chosen, we opted for df partial f with respect to x. If we had started off with partial f with respect to y, worked through this process, and then set it equal to partial f with respect to x, we would have gotten the same answer. All right. One second. Whoa, what is going on here? This is so weird. My keyboard froze. All right. So yeah, so you could have gone either way with that. So in this next one, I'll go, I'll choose the partial f with respect to y, just kind of mix it up a little bit. All right. So we already took care of the part in the previous page, previous video, if you will. We already took care of whether or not it's a conservative vector field. All right. So now it's a matter of actually finding a potential function. All right. So we'll take, like I said, whichever one we want, but I'm going to take partial f with respect to y. Right, because remember, let me just smidge this over just a tiny bit. Come on. That p is the same as saying partial f with respect to x. That q is the same as saying partial f with respect to y. All right, so I'm going to take the y, which is x cubed e to the xy plus 2y. We have that differential equation. Now I want to get it into differential form, which is really just, I mean, it's funny how things line up, but just this past week or so, 2 weeks ago, I went over this concept with my calculus students in high school, of the idea of getting a differential equation into differential form. And all it was is just multiplying both sides by dy in this case. And they're like, okay, I'm sure that's important to somebody. It doesn't seem like it would ever be. Here we are. And so partial f is equal to x cubed e to the xy plus 2y partial y. Integrate both sides. I gotta say that was probably the whole idea of multiplying both sides by a partial. In back in Calc 1, it's multiplying both sides by a dy. That was like my first real aha moment with calculus. It's like, oh, that's why you're allowed to integrate, right? Because it's if you move that over, you're integrating this one with respect to this variable. Oh, okay, so that's why that becomes an f. The antiderivative of one is some variable, and that variable is f because that's what the df says. Interesting. Little things. Anyway, finding the antiderivative of e to the xy. That's kind of fun. So you got to kind of sort of tackle that one. But fortunately, even though it looks ugly, it's really not that ugly. And it just seems that way. The derivative of e to the xy would be with respect to y, would be e to the xy times x. So let's just do that the other way around, right? Because x is really just a multiplier, right? So I have my x cubed as the constant multiple. I'm hanging on to that. So I'm going to multiply that by, instead of e to the xy, it would be 1 over x e to the xy, right? And you could just kind of test that out. You do a u sub if you want also, but you'd hang on to the 1 over x e to the xy times x, the x's would cancel, and you'd have, right? But basically, when you're thinking about it in the context of partials, really what you're saying is that you're taking the e to the xy, and instead of multiplying it by the derivative of the exponent, because that derivative of the exponent is constant, we're dividing it by the derivative of the exponent, right? Because again, it's so hard to kind of keep it in mind that x in this context is a coefficient rather than a variable. Right? The antiderivative of 2y is just going to be y squared, so that part at least. And this is going to be plus some constant function c of x. Right. So to go through the process of solving this, I would take my first order partial with respect to x now. I'm going to put the y. All right. But before I do that, I guess it might be a good idea to kind of clean things up. All right. So this would be x squared e to the xy plus y squared plus c of x. Now to differentiate with respect to x, we're going to do a little product rule over here. And the product rule for this expression. So that's going to be the first x squared times the derivative of the exponent, derivative of the second, which is e to the xy, times the derivative of the exponent, which is y, plus the second, e to the xy, times the derivative of the first, which is 2x. The y squared is going to zap away, no x involved there. And the derivative of c of x would be c prime of x. All right. So then you'd say, I wonder if there's any instance in which I would know, or any way that I could know the derivative, the partial of f with respect to x. And then you say, oh, wait a minute, there it is, right up here. If I can lock onto it. I'll get that equals p out of there. The highlighter out of there. So this is what we said before it was equivalent to. And this is what we're saying now it's equivalent to. All right. So it kind of probably, anyway, is a good idea, usually, to clean up a little bit just to make life a little easier. So this is x squared y e to the xy plus 2x e to the xy plus c prime of x. All right. So we have some consistency here, which is great. It doesn't always play out this way. You usually get a variable to cancel. It doesn't always happen that pretty much all cancel. But we'll rewrite x squared y e to the xy plus 2x e to the xy plus c prime of x is equal to 2x e to the xy plus x squared y e to the xy. All right, so that gives us a full-blown cancellation here. X squared y e to the xy, same. 2x e to the xy, same. We're looking at c of x, or c prime of x, is equal to 0. Now I need c of x. So again, that's the same as saying dc dx is equal to 0. So we're going to end up with something that's kind of nice. This is sort of the best case scenario when you have a problem like this that involves like a ton of writing to get to this point. So you're looking at dc is equal to 0 dx. Antiderivative of 1 with respect to c would be c, but it's really the function c of x. The antiderivative of 0 is some constant, but this is a function of one variable, so it's going to be an ordinary constant. So c of x is going to be equal to c. So this would be one of those instances where if you got to this step in the process here and you accidentally wrote plus c instead of plus c of x, you'd luck out and get the right answer if it's like multiple choice or something like that. But you'd get the right answer for the wrong reasons. So I would take my f function, which is x squared e to the xy plus y squared plus, instead of c of x, it's just some constant c. Right, so that's my potential. And so that essentially is the surface that has the gradient vector that's given by this vector equation. All right, so if you were to graph this and look to say, oh, gee, I wonder what the path of steepest ascent would be. You know, the greatest rate of change at a particular point would be, you'd figure out the vector of the gradient vector of this function, and then from there you'd maybe make some substitutions. You want to know at this point, that point, whatever, but you still have that c value that you need to figure out beforehand, which would require an initial condition. All right, so which we don't have. So there we are. All right, so let me stop that recording.